In this video, I will be discussing and analyzing the biomechanics of a front flip on a mini tramp. This includes the strengths and weaknesses of my execution through biomechanical principles. I was successful during my run-up/release into the air, and my weakness was my rotation, which affected my landing. The biomechanics that were involved in the strength of my front flip were projectile motion, Newton's third law of motion, and force summation, and the biomechanics that contributed to my weakness in the front flip: balance and stability, momentum, Newton's first law, and rotational inertia. I will also be explaining the anatomy, which includes joints, bones, and muscles that are involved in the front flip. The main joint involved in the anatomy of a front flip is the knee joint, which is a hinge joint. The bones that surround it are the femur, the fibula, the tibia, and the patella. It uses the hamstrings and the quadriceps to flex and extend it. My strength in completing the skill was my run-up and release into the air. My stage of learning during this part of the flip was autonomous, meaning that I was very confident in this part of the skill. This was a strength in executing the front flip, as I utilized Newton's third law of motion well, and I also applied the factors of projectile motion to launch myself into the air correctly. Newton's third law of motion can be explained by the phrase, "every action has an equal and opposite reaction." This can be applied to jumping on a trampoline, as the force that you apply or push into the trampoline will be applied back onto you, and the tramp will push you back, launching you into the air. To generate force, I run up to the trampoline and then jump into the air. As I'm about to land on the tramp, I begin to flex my knees. My knee is a hinge joint. It is also known as a synovial joint, and the main bones surrounding it are the femur, the fibula, the tibia, and the patella. To flex my knees, I need to contract the agonist muscles, which is the hamstrings, and relax the antagonist muscle, which is the quadriceps. This allows me to exert a larger force on the trampoline when I extend my knees. However, I feel like I could have flexed my knees more, which would have allowed me to exert more force on the trampoline. To extend my knees, I need to contract the agonist muscle, which is now the quadriceps, and relax the antagonist muscle, which is the hamstrings. If I extend my knees at the right time, I can use force summation, which occurs when all body parts move at the same time, to generate a large amount of force. If sequenced correctly, the strongest muscles closest to my center of gravity move first, followed by the smaller, weaker muscles. Extending my knees, along with the force I had built up during my run-up, creates the force that I push into the trampoline. Due to Newton's third law, the trampoline will apply that same force back onto me, which is what launches me into the air. A combination of multiple factors as I land on the tramp determine my projectile motion. The next biomechanical principle that helped me be successful in my release into the air was projectile motion. Projectile motion can be described as any object that is released into the air with a predetermined flight path. There are 6 factors that determine this flight path prior to the object being released into the air. These are speed of release, height of release, angle of release, spin, gravity, and air resistance. My use of projectile motion was successful mainly due to my speed of release and my angle of release. Speed of release is important because it determines how much force will be exerted on the object when it is released, and therefore is key in controlling the distance that projectile travels. In this case, the speed in which I run into the tramp will also determine how far I will travel while executing my flip. Also, due to the elevated angle of the trampoline, some of the speed and force created during my run-up will result in an upward force, which could help me control how high I get launched into the air. I start to accelerate into the tramp, but then I maintain a comfortable speed so that I don't travel too far horizontally. I also don't go too slow, which would mean that I wouldn't have enough speed and force to launch myself off the trampoline with enough height and distance to complete the full rotation of my flip. The next factor that was important in my successful use of projectile motion was my angle of release. Angle of release controls the angle that the object is launched into the air. A higher release angle will result in the object traveling in the more vertical direction compared to the horizontal direction. I was successful with my height of release because I set my projectile motion off on a large angle to give myself enough height to complete the full flip. When combining my speed of release and height of release, along with the other factors, I was able to be successful in launching myself with an appropriate height and distance to allow myself to complete the flip while also landing safely on the mat. I also had weaknesses during my front flip. This weakness was my rotation, which resulted in a bad landing. In this skill, my stage of learning was associative, as I could complete the skill correctly most of the time, but I still had to actively think about my rotation while completing the skill. This was a weakness, as I had too much rotational inertia and momentum, which meant that I was not balanced and stable during my landing. Rotational inertia can be described as the measure of an object's resistance to change its rotation. Rotation about an axis is known as angular motion. The front flip as a whole is called general motion, as I use a combination of angular and linear motion to execute the flip. The further away the mass of an object is distributed from the axis of rotation, the slower the object will rotate. Using this knowledge, after leaving the trampoline at the start of my flip, I don't tuck, which allows me to slow down my rotation as my mass is distributed further away from my axis of rotation. Spinning slowly allows me to control my flip as I can see the landing for longer. Next, I begin to tuck, so that my mass moves closer to the axis of rotation, which means I rotate faster. However, my weakness in this part of the flip is due to me holding the tuck for slightly too long. This meant that I over-rotated and spun faster for longer than I had planned. Ultimately, this is what caused my landing to be unbalanced and unstable as I had too much momentum coming into land. As a result of my mediocre application of rotational inertia, I had too much angular motion and therefore too much momentum coming in to the landing to execute this part successfully. Momentum is the product of mass and velocity. The heavier and faster you are moving, the more momentum you will have. Momentum is linked to inertia, and according to Newton's first law of motion, the more inertia or momentum that an object has, the harder it is to stop. In my front flip, I gain momentum from both linear and angular motion. This means that a contribution of moving forward and my rotation add up to get my total momentum. As I rotated for longer than anticipated, I spun faster, meaning that I had too much momentum for me to land cleanly. To try to stop my momentum, I had to lift and extend my right leg out in front of me by flexing my hip, which is a ball and socket joint, using the agonist psoas major muscle located above my pelvis in the lower back, and the antagonist hamstring muscles located below my pelvis on the posterior side of my body. I do this in order to provide an opposite force as an attempt to stop my momentum. Despite this, my momentum overcomes the force of my front leg, and I am forced to take a few small steps to decelerate and come to a complete stop. Another biomechanical principle that was affected by my over-rotation was balance and stability. Balance can be defined as your ability to control your body without movement against gravity. Stability can be defined as your ability to control your body during movement. There are three factors that contribute to being balanced and stable: basis of support, center of gravity, and line of gravity. Basis of support is the area within an object's point of contact with the ground. The bigger the basis of support, the more stable you'll be. The center of gravity is the center point of an object's mass, around which the rest of the object is equally balanced. This point is also the axis of rotation in an object. Line of gravity is a vertical line that passes through the center of gravity to the ground. An object will be balanced when its line of gravity falls within its base of support. As the line of gravity moves closer to the edge of the base of support, the more unstable the object will be. Due to my over-rotation, I extend my right leg out in front of me to increase the size of my base of support. This makes it harder for my line of gravity to move out of my base of support. However, my momentum carries my line of gravity outside my base of support, causing me to take a few small steps forward to regain my balance and stability. I also flex my hips again to lower my torso, as the closer my center of gravity is to the ground, the more stable I will be. Once I have come to a complete stop, I am able to stand up straight as I am confident that my line of gravity falls within my base of support. To improve my front flip and move from the associative to the autonomous learning stage, I need to be able to tuck for less time to slow down my rotation and reduce my rotational inertia, allowing me to be balanced and stable when I land.